Okay.
Okay.
I am in presentation mode. Can you see my presentation
Yeah,
in presentation
I can
mode?
see your presentation, and you can start now.
Okay.
Great. Good morning, everyone. It's our greatest pleasure to join this annual Focus on Microscopy conference in 2022. Although this year, once again, we have to do it remotely. So today, we will have our tutorial first given by Professor Manuel Martinez-Corral from the 3D Imaging and Display Laboratory in the Department of Optics, University of Valencia in Spain. And the title of his presentation is Fourier Lightfield Microscopy. And so this tutorial will last for 2 hours and 15 minutes. I suppose during this we will have have 1 or 2 breaks depending on manuals, depending on how we're going. And yeah, let's welcome Professor Martinez-Corral.
Okay, thank you very much. Thank you for the presentation. I'm gonna give my talk about recently reported microscopy technique. Fourier Lightfield microscopy is a technique which is mainly aimed for producing three-dimensional images of dynamic samples or dynamic specimen. This is made at the cost of some loss in resolution. Okay, I think I will explain that along the next 2 hours. So my first slide, I would like to remark the milestones in the development in Lightfield technology. In fact, Lightfield technology was reported much more than 100 years ago. So Liebman, at the beginning of the 20th century, he reported the first description of this technique, which at the moment was named as integral photography. Many years later, Adelson and Wong reported for the first time the mathematical description of this technique and gave to the technique the name of a Plenoptic technique, and therefore the Plenoptic function. Some years later, people from the University of Stanford, Ren Ng, and from the team of Liboy, they reported the Plenoptic camera, a monocular camera with the ability of collecting three-dimensional images in real time. And 1 year later, the Lightfield microscope, based in the same concept, which I will explain along the day. Okay, there are many other milestones. Let me remark our own contribution to this field. And then about 5 years ago, we proposed for the first time the Fourier Lightfield microscopy technique, which is the one I'm trying to make the tutorial today. So then to start, let me start from the very beginning. Let me start by analyzing how a conventional photography camera works. So here we have a very simple scheme of a photography camera. We have the object, the scene we are photographing. We have the camera lens, and here we have the sensor. Okay, by that time it was a photographic film, and now there's a CCD or CMOS sensor. And you can see that from every point of the object, emit a diverging beam of rays. These rays are collected by the camera lens, and they are focused onto the sensor. Specifically, there is a correspondence between any point of the object and the corresponding pixel of the sensor. And this process can be represented mathematically through the radiance map, also named a Plenoptic map or Lightfield map. What is this? This is a function. Okay, in fact, it's a 4-dimensional function, but here I'm making everything in less dimension in my representation. So we have spatial coordinates associated to any ray and angular coordinate. And therefore, for example, we can see that the central pixel is collecting rays that are passing through a singular value of the spatial coordinate, x prime, but which have a band of angular values or angular inclination. So in fact, what is collected by let's say the blue pixel of this camera is this plenoptic information. Single spatial value, a band of angular values. But what happens? What happens is that any pixel of the camera is integrating all the rays that are incident onto it. And therefore, the photography, what we know by a 2-dimensional photography, 1-dimensional here, is the integration of the plenoptic function. So here we have 2-dimensional information, x and theta, and here we have integrated over theta. And this is the photography. So we can see that conventional photography, conventional imaging, due to the integrating capacity or capability of pixels, in fact, what we are obtaining is the projection of the light field over the spatial axis. So it means that, in fact, conventional photography, conventional systems do not have good ability for collecting 3-dimensional information because they are losing the angular information. So a solution for this was proposed by Lippmann in 1908. What he proposed was quite simple, was the following. Instead of using a single objective, he proposed the use of a microlens array, which was set in front of the sensor, by that time a photographic film, now a matrix sensor. And okay, here we have the 3D object. We make the conjugation between the sensor with one plane of the object, and therefore we call it reference object plane, one plane in the middle of the object. And what we see is that this camera is collecting a series of 2-dimensional images, each with a different perspective, but different but conical perspective. What means conical? Means that closer objects provide bigger images, and when they go further, the images are getting smaller. So this is conical perspective. And this process can be represented in the plenoptic function, as before we did. But now the plenoptic function is different. Let's have a look to it. For example, this corresponds to the central image, what we call the central elemental image. We can see that all the rays are passing through the same spatial point, same value of x, but they have a different angle, different inclination. And the inclination is determined by the pixel that is collecting the light. So in fact, we can take all these pixels and put here, therefore then a column in the plenoptic function is one of the conical elemental images. If we go to the neighbor elemental image, this is represented here in this other column. So a column in the plenoptic function is an elemental image with conical perspective. And what happens with rows in the plenoptic function? So we can see here, we can see that every pixel that are placed in the plenoptic function in the same row, they have in common that they have the same angular inclination. They correspond to rays with the same angular inclination. Okay, so they have different x coordinate. They impinge onto the microlens array with different x coordinate, but with the same angle. But this is also an image. This is what we call a sub-image, micro-image, or orthographic image. Why orthographic? Because you can see that in this case, since all the rays are coming parallel to each other, in this case, the image I compose here, I will show now how I make it. They have orthographic perspective. It means that the magnification is the same, doesn't change with the distance to the microlens array. So how does this work? So then, for example, we have here many elemental images, many elemental images. So many columns, many elemental images. So let us suppose that I have 4 elemental images, each one with 5x5 pixels. So then I have 4 elemental images, 4 different perspectives, but conical perspective. And then what I make now is a kind of pixel mapping. I take, for example, all the pixels that are in the center, and with them I compose a new image, this one. So this is a micro image. It has orthographic perspective, and then from 2 images with 5 pixels, I can compose 5 micro images with 2 pixels. Here we have conical perspective. Here we have orthographic perspective. So let me show you one example. So this image was obtained in our lab quite simply. We didn't use a microlens array. We use a digital camera, which was mounted in a rail with in which with a motor we could move the camera to different positions, and then we obtained 7 by 7 elemental images. They seem to be the same, but are not exactly the same because they have different perspective. So first thing we can make with this information is to watch the scene from very different perspectives. And now we can apply this algorithm. And from these 7 by 7 elemental images with 300 pixels each, we can obtain 300 x 300 micro images with 7 pixels here each. So here we have few images with a lot of pixels and conical perspective. We have here very few images. A lot of images with few pixels and orthographic perspective. So here in the left and here in the right, we have exactly the same information, but organized in a different way. And what can we make with this? So first thing we can make is to implement an algorithm of refocusing. How it is working? So the algorithm works in the same way as the optical system. Let me show you. Let us suppose that here we have a system for collecting elemental images. So we have the sensor, we have the microlens array, we have a 3D object, and I fix my interest in 2 of the points of the object. And we can see that any point is let's say printing the corresponding pixels in the elemental images. This is the collection, but we can now display the 3D object. How do they make? So now, instead of having here a sensor, now we have a pixelated display, same size. Here we have the same microlens array. Then we illuminate exactly the same pixel as printed before, and we can see that here it is obtained a collection of ray beams that are intersecting in a given way. So if, for example, I make this experiment physically, and I put here, for example, a sheet of paper, then we can see the following. So we can see that if I move the paper, I can see that in this plane, we have 2 blurred images of point A and B. And here I can reproduce point object B, while A is blurred. And here I can reproduce object A, while B is blurred. And here everything is blurred. So it means that optically, I can reobtain the original object with some loss in resolution, but this can be done also computationally. How it is made? So this is the algorithm that make this. So here in this place, upper left, what we have is a scheme of a collection experiment of integral imaging. So there is some object here, and the light proceeding to the object is printing the pixels. And now from these pixels, we can obtain the plenoptic function. So, for example, this vertical row, the blue row, corresponds to this elemental image. Green row corresponds to this elemental image. And now I want to reconstruct the ray structure not at this plane, because this function tells me how is the ray structure in this plane. I want to reconstruct how it was in a different plane, for example, in this. And we can see that when I go from this plane XO to this other plane, theta, we have that the angles doesn't change. The angular information is the same, but spatial information is different. And spatial information has changed proportionally to the distance. And this mathematically is represented by sharing the Lightfield function. So I can move my reconstruction plane in this direction, and I can calculate how the ray structure was in a different plane. So I simply need to share the plenoptic function proportionally to the distance. And finally, this is the representation. And finally, we can obtain the picture in this plane by simply integrating the plenoptic function. Okay, let me explain you in a different way. So how this algorithm is usually implemented? It is implemented in the following way. So in fact, the algorithm is an algorithm in which we take the elemental images, original elemental images, we shift an integer number of pixels with respect to each other, and later I sum the values of the pixels. For example, this situation, ns is number of pixels shifted. This situation corresponds to reconstruction in this plane. So we simply have all the elemental images places one neighbor to the other. And now I collapse. I shift all the elemental images toward the center by 1 pixel. And this corresponds to reconstruction in this other plane. And then I shift 1 additional pixel. And this corresponds to the next plane, and so on. So you can see that the planes in which I reconstruct the function are not placed proportionally to the number of pixels. There is a non-linear relation between the actual coordinate and the number of pixels shifted. So this is something like that. Okay, here I don't have as many planes as here. And okay, so this is an example. So then I had here 7 by 7, and then I started to collapse all the elemental images towards the central one, 1 pixels, 2 pixels, 3 pixels, and so on. And finally, to sum. Summing is equivalent to make the integration we did in the algorithm, and this is what we obtained. So this is also the information that we have in the collection of elemental images. So we have many perspectives. We can calculate the orthographic views, and we can calculate depth reconstruction. All this information is here. So this is, let's say, the primary proposal of this technique. This can be implemented in in real setups by, we did in our lab with a single camera, a moving camera, but in other labs they have implemented this method by combining and synchronizing many cameras. You can see that when you have many cameras and you have the object in front, this object is captured with high parallax, with high disparity. So the parallax angle here is very high. But this system is very bulk. So this is good, but it can be used only in case you can afford this kind of bulky systems. So in order to avoid this problem, the Lightfield or Plenoptic camera was proposed. So the concept is more or less the same. It is useful in case you don't need big parallax. For example, this is a conventional photographic camera. What you make is that you insert a small microlens array just at the image plane. You move the sensor a little bit so that now the sensor is conjugated with the camera lens. And therefore, this is another way of collecting spatial and angular information, because you can see that here we have, for example, these blue rays. All of them have the same spatial information, but different angular information. So when you implement this system, the conjugation relations are important, because the sensor must be conjugated with the camera lens, and the microlens array must be conjugated with the object. So let me show you in terms of the Plenoptic function or Lightfield function. So you can see here we have the object. The object is emitting ray beams. This angle is the parallax angle. This is small because this scan is in distorted scale, but in fact usually this angle is very small. So what we are collecting, for example, here in the red column, here we have all the rays that are passing through this point and have different angles. So this is a micro image. And if you apply some simple matrix, ABCD matrix formalism, you can see very easily that the Plenoptic map, the Lightfield map here, is approximately the same as the Lightfield or Plenoptic map emitted by the object, but with different scale. For example, here spatial magnification is smaller than 1. So big space here is small space here. Conversely, the angular magnification follows the opposite rule. So here we have small angles, and here we have bigger angles. But apart from it, what we are collecting is scale version of what it was emitted. But we can wonder, and what is happening here? What is happening here? And here we can see that a kind of 90 degrees rotation is happening. Because, for example, we can see here all the rays passing through the central point in this plane. In fact, they proceed from different points of the object. So we can see that what it was a row here now is a column here. So going from the object plane to the camera lens plane computationally can be made by simply rotating the Plenoptic map by 90 degrees. Okay, it's rotation plus some sharing plus some scaling, but basically it's a 90 degrees rotation. And we can see here that in fact this system is totally equivalent to have here an integral imaging system with the lenses placed here. Okay, so here this is now shaded. So this is the system, and this is the equivalent system. So in fact, the Plenoptic camera, the Lightfield camera, is making something quite similar to the integral imaging system, but in a different way. So Plenoptic camera provides us the same information as an integral imaging system, but let's say in 2 steps. Then we need to capture and then to rotate. So now we have here the elemental images as we had before. So let me show you an example. So this is another example obtained in our lab. This is an example, an image obtained. Okay, let me tell you something here. So here, in fact, the vignetting is very important in order to avoid the overlapping between the micro images. So micro images do not overlap, provided that the numerical aperture of or f number of the camera lens, so this angle, is the same as the f number or numerical aperture of the micro lenses. And then is this way is the own aperture stop of the camera lens, which avoids the overlapping between the elemental images. So if you arrange properly this system, you have that this is the image obtained with the camera lens, with a Plenoptic camera. These are the micro images. And this is the algorithm of the pixel mapping I showed you before, but we can apply it in the inverse direction. So we can calculate from the micro images, we can calculate the elemental images. So from this information captured with the Plenoptic camera, we can calculate a collection of elemental images, each with a different perspective information. So sorry for the quality of this movie, but now, okay, the number of pixels of the elemental images is very low in this case. Yeah, you can see that in the Plenoptic camera, we have a single sensor which is receiving all the information, and therefore resolution here, pixel resolution, is worse than in the case of using a collection of digital cameras. Of course, from this information, we can also calculate, because all this information was here. So we can see different views, we can calculate depth refocusing information, and so on. Everything is here. We have, in this 2-dimensional, let's say, matricial image, we have a 3-dimensional information. But, okay, let me go back. Which is the main problem of the Lightfield camera? The main problem of the Lightfield camera is the poor parallax angle, because we are collecting rays with very small, with very poor angle. And this is not good, because we have a very poor angular information, very poor perspective information. We cannot see the scene from large perspectives, very narrow perspectives. But where there is no this problem, we don't have this problem in microscopy, because, okay, here we have a, let's say, single scan of an optical microscope. And what we see here is, okay, this is the objective, This is a tube lens. So usually in a conventional microscope, what we have here is the object plane that is in the front focal plane of the objective. There is a telecentric arrangement between the objective and the tube lens, and therefore and here we finally we have a microlens array. I'm sorry, CCD. We can remove this. We have the CCD, and okay, we obtain here a highly magnified image of this, but we can see that the angle under which the object is seen now is very high. In fact, it depends on the numerical aperture. The higher the numerical aperture of the objective, the higher the angle under which we are watching this object. So, a conventional microscope is an optical system in which we can receive light proceeding from the object, but with a large perspective angle, with large angular information. And therefore is good candidate for applying on it the Lightfield concept. So before that, let me make some numbers. Okay, this is a microscopy conference, so every one of you knows this, but let me put it in a slide. So I will call this microscope as the native microscope. I call it native because over this microscope, later I will insert things. So, for example, let us suppose that I have an objective with a NA numerical aperture 0.4, magnification 20x. Let us suppose that I at least for my calculations, I consider monochromatic illumination of 0.6 micrometers. And let us suppose that, for example, the pixel size is 2.2 micrometers. So, resolution. The resolution of an optical system is determined by the combination of two effects. The diffraction effect, this is the quite classical Abbe formula for resolution, and the pixelation effect. This is the formula of the Nyquist limit. And therefore, we combine the two effects, and we see that, for example, this microscope has a resolution limit of about 1 micron, and a depth of field, which is governed also by a formula that depends on the pixelation and also on the diffraction. So we have about 1 micron of resolution limit, about 8 microns of depth of field. Let me remember, I know that many people get confusion about this. This is the resolution limit, minimum distance that we can have between two emitting points so that we still can distinguish them. This is resolution limit, about 1 micron. Usually, resolution is measured through the USAF resolution chart. And in this case, it's sometimes common to use the line pairs per millimeter, which is just the inverse of the resolution limit. Okay, this is another way of explaining resolution. We can see about 1,000 line pairs per millimeter in this example. Okay. Now we go. So, in order to take profit from the concept proposed originally by Lippmann and later by themselves, Levoy's group proposed in 2006 the Lightfield microscope. And it was very, very simple. It's simply, okay, very simple, the draw, the scheme. Implementation is not that simple, but not difficult. You simply insert a microlens array in this plane. and you displace the CCD towards or till the back focal plane of the microlenses. Okay, and in that way, as I showed you before, in the Plenoptic camera, you can collect spatial information. So, for example, in this case, we have all the rays passing through this point, in fact, proceed from the central point of the object, and the pixels are collecting the angular information, different pixels, different angle. This microscope was named later as Plenoptic microscope or integral microscope. And as I explained you before, perspective images are not captured directly. In fact, this plane, okay, relations. So microlens array is conjugated with the object plane, and on the other hand, the sensor is conjugated with the aperture stop. So it is the aperture stop which is avoiding the overlapping between micro images. So it means that, in fact, in order to implement this microscope, we need to use, we need to use a microlens array such that its numerical aperture is the same as the numerical aperture of the microscope, but evaluated here. So let me show you this scheme with the Plenoptic map. Here we have the micro image. This is what we collect. For example, the blue micro image will be there. Here we have spatial information, we have angular information, and there is strong rescaling between what we are collecting and what was emitted. We have a rescaling, but not rotation. So what here is a column, here is still a column. You know that a microscope have strong spatial and strong spatial magnification and opposite angular magnification. So big angles here means very small angles here. So as I told you before, what about the Lightfield microscope? So we need to take care about conjugations, I told you. Second, we need to take care about numerical aperture. The numerical aperture of the microlens must be the same as the numerical aperture of the microscope as evaluated in this space, which is the magnified value of the numerical aperture as evaluated in the object space. Another problem, another question that is very important in Lightfield microscopy is that Lightfield concept is based in a ray optic concept. So it is based in the fact that we assume that this pixel is collecting a ray that has, a ray that has a given inclination. But this assumption is not true if we have strong diffraction effect. What means strong diffraction effect? It means that if the point spread function of the native microscope is large, is big, is comparable to the microlens size, then in that case, the Lightfield concept doesn't work. So then we cannot assume that a given pixel is collecting a given angular information. So, I'm sorry. So there is a rule. A rule is a kind of heuristic rule. It says that the microlens, any microlens must be at least 5 times bigger as the ARIDs than the ARIDs as evaluated here. And this is parameter mu. Parameter mu evaluates the quotient between the pitch of the microlens array and the radius of the ARIDs as evaluated here. It must be bigger than 5. And then in this case, everything works. Lightfield concept works. Resolution is mainly determined by, not by diffraction, but by the pitch. And then it works. And finally, remember that the angular sampling is determined by the number of pixels behind each microlens. So it's important also to fit many pixels here. So let me make some calculations. Therefore, I'm going to implement here in the paper a Plenoptic Lightfield microscope. So first, we need a microlens array. So, okay, there are many microlenses manufacturers. The one, this is a tutorial, I can say that. The one, we have some which are manufactured by this company, which is in Germany. Okay, they have good microlens arrays. Their stock is good, and they can provide you approximately anything you need. So remember, we need to match the microlens array with the objective. So let us suppose that we use this microlens array from the stock of this company. We use this objective I told you before, this pixel array. First, we check if there is good matching. So I evaluate the numerical aperture of the microscope, the native microscope here. It is 0.5 divided by the magnification, 0.02. There is good matching with this microlens array. Okay, everything works. So we are working in this scheme. Second, I check if the condition mu bigger than 5 is working, and therefore we have no problems with diffraction. Okay, we calculate, we have 5.3. And therefore, with this, we obtain the following. Remember that we had the spatial resolution limit of the native microscope before inserting the microlens array was about 1 micron. Spatial resolution now of this microscope, of this Plenoptic microscope, is almost 9 microns. So there is a resolution loss factor of about 9. So this is the price we are paying for having three-dimensional images. We are losing resolution by factor 9. So this is one example, but whatever the example you look for in the literature, you find this resolution loss, about 10. So no more can be made in the image capture here. So I'm showing here one example made in our lab. So we have a fluorescence experiment. These are the fibers of cotton fibers. These are the micro images captured directly with the Lightfield microscope. You can see these are the micro images. Micro images are not circular pixels because there is angular information within any of the micro images. From this information, we can obtain all this information: perspective and also depth reconstruction. Okay, so but this tutorial is not about Lightfield microscopy. It's about Fourier Lightfield microscopy. So let me make a final summary of Lightfield microscopy features. So a Lightfield microscope, the one proposed in 2006, permits the capture after a single shot of the spatial angular information of the rays emitted by 3D specimen. Single shot. It means that you can obtain three-dimensional images of dynamic samples. It has the lack of flexibility due to the numerical aperture matching between the microlens array and the objectives. It means that if you have a microscope and you change the objective, you need to change the microlens array. Not explain it here, but the system is not shift invariant. So actually, it cannot be defined. A point spread function that can be used for all the field of view. So you can define a small region by small region, the corresponding point spread function, but the system is not shift invariant. You cannot have a point spread function common for the full field of view. Spatial resolution is 4. There is a resolution loss factor of about 10. Not shown here. The depth reconstruction has no homogeneous lateral resolution. So lateral resolution, when you obtain the depth reconstruction here, is not the same. It changes plane by plane. There are good planes and bad planes, and the number of refocusing planes. These last 3 drawbacks can be partially overcome by computational methods. But in my opinion, this is personal opinion, computational methods cannot actually recover information that was not captured. So with computational methods, you can improve quality of image, but the frequencies which were not captured, you have lost it forever, unless you have much more information about the sample. So it means that, okay, it is of great interest, the conventional light field microscopy, but it would be nice to find another technique able to avoid these drawbacks, mainly able to avoid the problem with resolution, at least partially, or to avoid the problem of the system is not linear and shift invariant. Okay. Anyway, what I told you was a personal opinion. Even currently, there are many groups still working with the conventional light field microscopy, the one reported in 2006. They are providing, reporting very nice results, which are published in very nice journals. So if you want to follow the light field microscopy contributions and the light field microscopy progress, you still can follow. For example, in this summary of contribution I have collected for this course. So I would say, that mainly in the past few years, everything that is made is computationally. Proposals are based in computation. So, and this is what we proposed 5 years ago, and the aim of this tutorial. This is the Fourier light field microscope. So remember, this is the light field microscope. So we have here the light field collected here, which is a scale version of the light field emitted here, with high spatial magnification and high angular demagnification. But equivalently, as what we explained before in the Plenoptic camera, we could calculate very easily how is the Plenoptic map here. So, and it is not difficult to find that the Plenoptic map here is the same as the emitted Plenoptic map or collected Plenoptic map, but rotated by 90 degrees. Rotated by 90 degrees. So Okay, not only rotation plus some scaling, but forget about this, mainly rotation. And therefore, it means that the columns here are now rows. But we don't make this computationally. We can make this optically. We can capture directly this plenoptic map if we don't place the microlens here at the image plane, but we place the microlens array at the Fourier plane, at the aperture stop. And therefore, we will collect directly this function. And this is what I show in this quite simple scheme. So this is the microscope objective. This is the object plane, let's say the reference object plane, because our object will be 3D. There will be many object planes, but this is the reference object plane, which is placed at the front focal plane of the microscope objective. This is the aperture stop. We have telecentric arrangement. The aperture stop is at the back focal plane of the objective. And we insert here the microlens array. And we can see, for example, that the central lens, then we have the conjugation. In this case, the conjugation is made in such a way that the sensor is conjugated to this plane. And therefore, we can see that what is collected here is the image of this with a magnification that is the quotient between this focal length and this focal length. And we can see that within the depth of field of the instrument, all the planes that are behind or are in front of the reference object plane are printed here, are imaged here with the same magnification. You can see that this cylinder, all of it is imaged here with the same magnification. So we are collecting with the central microlens orthographic images of part of the object placed in this cylinder. And what happens with the upper microlens? It is collecting with the same magnification images of all objects or plane objects that are here in the red cylinder. So here we have orthographic perspective of the object placed along this direction. And this angle would be the parallax angle, which depends on the focal length of the objective and also depends on the pitch of the microlens array. So, but this is an example. Naturally, here we have a 1D projection of the system. This is, and here we have the 2D. So if you have 3 microlens array that are fitted into the aperture stop, then you have 3 elemental images, but in the full aperture stop, you have 3, 2, 2. You have up to 7. Okay? So this is an example of what you can capture directly with a Lightfield microscope. And you have these images directly. You don't need any additional processing. You don't need any numerical aperture matching. I said nothing about the numerical aperture of the microlenses. In fact, the numerical aperture of the microlenses only has interest about the field of view, not other thing. And let me make some numbers. So I told you total magnification of this system, quotients of focal lenses. Number of elemental images. The number of elemental images is the quotient between the diameter of the aperture stop and the pitch. And we can obtain the diameter of the numerical f-stop from the numerical aperture of the objective and the focal length. The field of view is the the quotient, the conjugate of the pitch. The parallax angle, this angle that I told you, the parallax angle between neighbor elemental images. It depends on the pitch and on the focal length. You can see that, in fact, any of these elemental images are being collected with a numerical aperture that is smaller than the native one. So the effective numerical aperture with which the elemental images are collected is the result of dividing the original numerical aperture by the number of elemental images that you are collecting. Elemental images along a line. And the good thing is that any of these elemental images in the region of interest is linear and shift invariant. Not only 2D, but 3D, linear and shift invariant. And it means that the use of the convolution protocol is quite easy. It's trivial. And you can use a point spread function for any of the elemental images, or a common point spread function for the integral image, for the collection, the full collection of elemental images. This is the same, and more numbers. Resolution limit. We can apply the same equations we applied for the conventional microscope. We can apply here for calculating the resolution limit of captured elemental images and the depth of field. But let me tell you that in fact, this is a scheme. This is not the real. This is not the real way we implement the Fourier Lightfield microscope. First, because in this scheme there is nothing that prevents for the overlapping between elemental images. We would need some field stop somewhere. So there are no optical barriers between elemental images. And second, in many microscopes, the Fourier plane is not easily accessible. Or maybe we can have a microscope in which we want it to work in Lightfield mode or in conventional mode. So it is a good idea to insert the microlenses here, not directly, but through a relay system. So let's say this is a more realistic scheme of the Fourier Lightfield microscope. So then we use a relay system here. This is a telecentric relay system. There is a conjunction of focal points, and therefore we have the conjugation. Object plane is conjugated with field stop, which is conjugated with the sensor. In order to avoid the overlapping between the elemental images, the conjugated of the field stop onto the sensor should be equal or slightly smaller than the pitch. And this is determining the field of view here. On the other hand, the microlens array is conjugated with the field stop. So the magnification of the relay is determining how many microlenses are we fitting here inside. So it's determining the number of elemental images. And when you determine the number of elemental images, you are determining indirectly the effective numerical aperture of the system, and therefore the final numerical aperture, the final resolution of collected elemental images. Let me tell you that in order to have enough images to make the depth rendering, we need to have at least 3, like in the scheme I showed you before. We need to have at least 3 images, at least 3. I think some authors have tried with only 2. So, okay, 3 along a line and 7. Some authors have tried fitting only 3, 1, 2, 3. So, but okay, I have not made this. So for the moment, I will try always to fit at least 3. And resolution loss then fall down till maybe a factor 4. So let me make some numbers. No, this is a tutorial, so we make some numbers. So first, the diameter of the field stop is the conjugated to the pitch of the microlenses, that is to the diameter of elemental images. So this is this equation, okay? And then this is fixing. Okay, you have to fix that in order to avoid the overlapping between the elemental images. And this is fixing the field of view here. Okay, second equation. Here we have the pitch. When we project virtually this pitch here, we have let's say a projected pitch which follow this conjugation equation. So this is the pitch of the microlenses projected onto that plane. And therefore, the number of elemental images is the quotient between the diameter of the aperture stop and the projected pitch. So then we can make some calculations. So which are the equations that govern this? So the native microscope I showed you before. The Lightfield microscope, 2006, Lightfield microscope. These are the equations. I haven't explained them, but okay, it is published everywhere. Elsewhere. And here the only condition is that mu should be bigger than 5. Okay, the microlens array must be 5, at least 5. The microlens pitch must be at least 5 times bigger than the AB disk, the point spread function over the microlens array. And these are the formulas I showed you before for the Fourier Lightfield microscope. And we make some numbers. For example, this is the microscope we are working with. So this is 20x, 0.5. So we can calculate the focal length of the objective. We can calculate the diameter of the aperture stop. This is the sensor we are using. This is the wavelength we assume, and we have taken one of the microlens array from our stock. This one. This is the one we are going to use, but there is a big flexibility on here. So we put here a microlens array with pitch 1 millimeter. Sometimes we would call it not microlens but millilens. Okay, but we call it microlens array. And this is the relay. Of course, in the relay you can change the focal length, but we have adjusted so that applying the equations, the number of elemental images here is bigger than 3. So, okay, we make the calculation and obtain 3.2. This is good because sometimes, there is some vignetting you cannot control. It is convenient to have here not exactly 3, so 3 point something. This is good. Therefore, the effective numerical aperture of our Fourier Lightfield microscope is, okay, the original one divided by the number of elemental images. This is the effective numerical aperture of any of the elemental images we are going to capture now. Okay, and these are the numbers that we obtain, okay? And we can compare then with the previous system. This is the native microscope. I did the calculations before. This is the Lightfield microscope. I think these are the calculations I showed before. And this is the Fourier Lightfield microscope. So you can see, okay, in fact, when you compare the depth of field, you cannot compare directly these numbers, because this is the depth of field for this resolution, and this is the depth of field for this resolution, and this for this. So probably if I wanted to find out, in this case, the depth of field for this resolution, we will have a much longer. Okay, so this is in fact the numbers we can compare. We can see that resolution is better. But the most important, we are still at a factor 5 from the native microscope. So, okay, we have 3D, but we are losing something. But, okay, but we have 3D in real time. And we have linear and shift invariance in real time. And we can change the numbers. For example, let's go further. For example, let's take this objective 40x, this numerical aperture 0.65, this wavelength, and for the native microscope, we calculate, we make numbers. Of course, we have higher numerical aperture. Now we have a better spatial resolution, and of course, shorter depth of field, because you know, the better the resolution, the shorter the depth of field. You can see that in a conventional microscope, the main impact over resolution, over depth of field, is given by diffraction. There is a small influence due to the pixelation, but diffraction is the one that governs. What about the Lightfield microscope, the conventional one, the one proposed in 2006? Okay. In this case, okay, we need to have good matching. The matching, okay, this is the objective. This is the objective. The matching would require that the numerical aperture of the microlens array would be the result of dividing the numerical aperture of the objective by the magnification. That is 0.016. And we also need this factor to be bigger than 5, the mu factor. Mu factor depends on, okay, if we want to think in the microlens array, according to the microlens array, the mu factor depends only on the pitch. So we need this number to be bigger than 5, and this number to be 0.016. So this is the microlens we should use for making this, the microlens array we should use for making this experiment. A pitch bigger, but not much bigger than 100, and a numerical aperture of the microlens array about this number. So let me tell you that we don't have this. We don't have this. I haven't found this in the stock of manufacturers. So somebody should build this for us. Maybe, I don't know, maybe you can find it. I haven't found it. So I should change this objective because there is no microlens array that there is no micro that fit this microscope objective. But okay, doesn't matter. Let's make calculation. So this is the resolution limit that could be obtained with this Lightfield microscope. This is the resolution limit. We obtain it with the conventional, the native microscope. And this is the resolution loss factor. So it is always about a factor 10. So nothing can be done about that. 10, 9, nothing can be done. And what about the Fourier Lightfield microscope? So, okay, let me make some calculations. Okay, so this is the calculations. So this is the magnification. This is the focal length of the tube lens, and therefore this is the focal length of the objective. So this is the objective we have taken from the shell. Numerical aperture, it means that this is the diameter of the aperture stop. Same sensor as before, same wavelength, and we use the same microlens array as before. We can make it. The only difference is that now, if we want to obtain this three, a value of this is NAA, EI. If we want to have a number of elemental images slightly bigger than 3, we have changed the focal length of the first of the relay lenses. Previously, we used 125. Now we are using 100. This is the only change we need to make. This is the effective numerical aperture, which is the result of dividing this number by this. And these are the numbers that we are obtaining according to the equations I showed you before. And then we can compare. This is the native microscope. Of course, now we have a, let's say, better objective, and therefore we have better resolution. The Lightfield microscope resolution is now better than before, but still quite poor. And now this is the resolution we obtain. Still not very good, but much better than this. The system is much more flexible and it's linear and shift invariant. And we have found that, in fact, due to the poor magnification, real magnification, we are working, in fact, with a microscope of magnification 2.6, the real magnification between this plane and this. Due to this poor magnification, in fact, at the moment, the bottleneck for obtaining the good resolution in Fourier Lightfield microscopy is the sensor pixel size. Then, for example, if we change this 2.2, if we could change by 1.2, you could see that this 3.4 would move to 2.4. So Fourier Lightfield microscopy is quite sensitive to the pixel size. So future development of Fourier Lightfield microscopy will be associated to the possibility of using sensor with smaller pixels. So this is the way. So then I finish numbers, and I would like to show you some results, the way we implemented this. So this is the first Fourier Lightfield microscope we implemented in our laboratory. It was quite simple. So this is the objective. Okay, here we had an optical filter. This is the relay. Okay, relay lens 1, relay lens 2. This is the field stop, which is placed here, trying to avoid the overlapping. Here was the microlens array. and here the CCD. Here the sample. For the case of the white light illumination for Lightfield, we put here a diffuser film because it was really very important to obtain illumination in which all the angles have the same weight, and this is for the green laser for fluorescence. Okay, this was our first. And these are, in fact, I showed you before this result. So as the first example, we use a regular cotton, which is nice because it provides some fibers, long and narrow, and we had many fibers in the depth of field of the instrument, and we obtained these 7 elemental images. So here the parameter n is equal to 3. As I showed you before, from them, first thing you can make is to put them in a movie, and therefore you can watch the sample from many different places, or you can make a depth rendering. So this depth rendering is made with the same algorithm I showed you before, but adapted to this case in which the images, the images obtained are orthographic, and therefore, for example, in this case, when you make a stack of all the elemental images, all with no displacement between them, this plane in the previous slide was the plane of the infinite. In this case, when you match all the elemental images, which in fact all of them are similar, you are reconstructing the reference object plane, and therefore you start to move all the images with respect to separate all the images with respect to the central one and to sum the pixels, and therefore you are reconstructing planes here. And if you separate in different direction, then you are reconstructing here. And in this case, there is a linear relation between the number of pixels of displacement, of shifting, and the distance of rendering plane from the object plane. So and then we could make this. So you can see that you can reconstruct very easily at different depths. And not place it here, but if you want to have more planes here, because you have here one plane, when you displace one pixel, next plane, if you can make the distance between rendering planes smaller, you simply need to resize the elemental images. For example, if you have one elemental image is, let's say, 300 pixels, you can computationally resize to 600, and then you will have double the planes. So a more dense depth reconstruction, but reconstruction time will be bigger. And there are many factors that are linked because everything is connected, but it's not difficult. And then I prepared a simple simple sheet in in Excel. So here in black are the parameters of the elements. So for example, we have a numerical aperture of 0.5, magnification 20x, focal length of the tube lens 200. This is our microlens array, Rayleigh lenses, pixel size, wavelength. Blue is calculated, let's say intermediate parameters, and in green are the figures of Fourier Lightfield or native microscope. And therefore, this is the example I showed you before. So with this objective, this microlens array, this relay, this pixel size, we could obtain this effective numerical aperture, this number of images, resolution in line pairs per millimeter, depth field, etc., etc. And I have a movie here. So, for example, I can change the numerical aperture and the microscope objective, and then I see that the number of images is not good. Then I change focal length of relay lenses, and now obtain the numbers I showed you before. So it's quite easy to have this kind of calculator in an Excel page. And not here, but for example, now we could try to change the pixel size and see the difference, or to change. But the good thing here is that everything is related. But I think that you don't need to have in your stock a big collection of microlens array. You only need to have, let's say, 1 or 2 or 3. And okay, to be able to change the focal length of the relay or something like that. Or you can work in such a way that everything is fixed. You only change this, and then you have here a range in which n is moving, for example, from 3 to 5, something like that. Okay? Because n smaller than 3, at the moment we do not recommend. Some authors have tried with 1.5, but at the moment we do not recommend. And I think in the last part of my tutorial, I think I'm going too fast. I'm sorry. In the last part of my tutorial, I will tell you how to set the Fourier Lightfield microscope in your lab. So remember that conjugation relations are very important. So, okay, everything should be element number 1, 3, and 6 must be conjugated, but this must be conjugated with this, and this, they must be at the distance, and this should be in a given distance, and so on. So how do we implement in our lab a Fourier Lightfield if you want to make in your lab? Okay, so let us assume that you know how to make or how to put all your elements vertical, perpendicular to the optical axis. So we define one optical axis, and let us suppose that we know how to make them to be perpendicular to the optical axis. So the first thing we make is we prepare a parallel beam. So here we have a laser with a fiber, a collimated lens, and then we prepare a parallel beam. And the optical axis of this parallel beam will be our optical axis. So then we prepare a parallel beam with a sharp plate. We make sure that the parallel beam is really parallel. You know, sometimes there are other ways to, with collimating systems or projecting onto a wall that is 10 meters away. Okay, let us suppose that you have parallel beam. We have the microlens array, and we have the sensor. And of course, first thing we need to make is to displace the sensor with respect to the microlens array to make sure that the sensor is in the back focal plane of the microlens array. So this is okay. This is quite accurate. This is quite accurate. So first step, and now we fix this. We fix this. So now we don't move this. We fix first part of our system in which microlens array and sensor are in the good distance. Second, the second thing we need is to insert the second lens of the the second lens of the relay system. So please make sure, okay, this is parallel, make sure that this is perpendicular to this axis, and then you have to move, you have to move it till you find this solution. Okay, only the central microlens is illuminated. So this is the bad position, good position, and okay. Third step, we need to fix the position of the field stop. And the field stop should be at the front focal plane of the relay lens. So then you have to move. Actually, you close it. You put it in a very close position. You move it, very narrow. You move it. And okay, here I show, this is not a movie. This is only one step. You move it till the borders of the aperture stop are really sharp at the sensor plane. You can check now that you can open it, you can close it, okay? You know here dimensions because you know the pixel size. You can try to fix now at the position so that since you know the pixel size in your monitor, you can see the size of this, and you can check that it is the same. It has the same diameter as the pitch of the microlenses. Next step. Next step is to fix the first lens of the relay system. So this is still parallel. We don't need to check every time. We make sure that this is perpendicular to the optical axis, and then we can move it. And here we have a double check. We have a double check. We can put here the shear plate, and then here we have a double check. On the one hand, when the relay lens is in the proper place, we have horizontal lines in the shear plate, and we have sharp images here. Okay, bad position and good position. And now we need to include. Okay. We need to include the microscope objective. So microscope objective must be placed in such a way that its aperture stop is in the front focal plane of here, and therefore would be conjugated here. Okay, and therefore we will have let's say many checkpoints. When it is in the good, good position, no, 2 checkpoints in the good position, then we have that the shear plate tell us that this is a parallel beam. Okay, and here we have only a single image of a sharp single image of the field stop. And now we put we insert the object. This is fluorescence. I haven't put it here. Here we should have a filter in order to avoid to have the incident light. We only need the fluorescent light. We could insert here a filter. So okay, this is blurred. So we can find when the image is sharp, and here we have a many as checkpoint. We have the sharpness of the image. We can check also how many microlenses are illuminated. So everything is now under control. So anyway, remember that I forgot to insert here a filter. Okay, so following this experimental procedure, my students used to set up the experimental system. It's not difficult, not a long time. Remember that in fact the object is 3D, so there is no single object plane. So we have a reference object plane, which is the one that is conjugated to the sensor, but the object is extended. You can move it actually, and depending on how on the movement, there will be a different part of the object that is in the reference object plane. So this is the experiment we did because in a given paper we propose an algorithm that is very effective, that is quite fast, and that it's very good when you are working with sparse fluorescent samples. So the algorithm is very simple because you make the same shifting, but we don't sum the pixel values, but you multiply. Then, for example, in this case, you multiply all the values that is in the same vertical position. And here you multiply all the values that are in the same vertical position. But this is quite fast. This is good because when there is no, let's say, convergence of rays in a given point, then when there is one low value, the multiplication make all the values to go down. And the good thing of this is that you can obtain optical sectioning in real time. So this is a movie obtained in real time. So we were moving in real time the position of the object. For any step of the movement, a different part of the object was in the reference object plane. And therefore, what we did was to apply this algorithm, but we applied this algorithm not for all the planes, but only for the reference object plane. So we didn't calculate all the 3D. We calculated only this, which is represented here. So totally real time, you can see with optical sectioning different planes of a sparse fluorescent sample. Of course, you can record everything and you have all this information. So for any position, for any axial position of the sample, you have the optical sectioning in a plane, or you can have the 3D image with optical sectioning, but it takes more time. So you can make many things in real time, and you can store this information, and you can many things offline. The good thing of Fourier Lightfield is that you can make use of all the facilities of your microscope to make Fourier Lightfield. One example is dark field. So if you have a microscope and your microscope has dark field facility, you can make dark field Fourier Lightfield microscopy. You simply need to, you insert, let's say, your Fourier Lightfield add-on, and you obtain Fourier Lightfield microscopy in dark field mode. You can take profit from all these facilities, for example, this. And this is one example. This is one experiment we did some time ago. These are the elemental images of soap bubbles. And this is what we obtained. So this is this is a transparent sample. And this is the experiment with this with the Drosophila. And you can see that with these elemental images, of course, your resolution has fallen by factor 1, 2, 3, 4, 5, 6. So if you can afford to lose resolution by factor 6, but you are interested in having real-time 3D, so this is a good system. This is also made with dark field. By finishing, let me tell us that we founded a spin-off named Do It Plenoptic. So the product that we have, our first product, is the add-on, which inserted in the eyepiece port or in the camera port, convert your microscope into a light field microscope. So these are some of the images obtained with this microscope. This is a bright field image with microfoam. This is bright field also with a chip condenser. Naturally, here nothing is moving, so this is a time is stopped. So this is not dynamic. This is dynamic. These are the elemental images obtained with light field microscope of living phytoplankton. And this is image using the dark field illumination mode. So you can obtain in real time this two-dimensional information and also this three-dimensional information. Of course, you can make particle tracking and many other things, and depth measurements, and so on. So yeah, let me tell you that the combination between dark field and Fourier light field, I think is very promising. This is another another result obtained with Fourier Lightfield microscopy. Okay, the cellular walls were of interest in this case, and you could obtain in real time. Of course, you are losing here 1, 2, 3, 4, 5, 6, let's say 7. So it depends on the resolution you need. Fluorescence. I haven't shown you more algorithms, shift and sum, shift and multiply. These images are the results of using a deconvolution algorithm, 3D deconvolution algorithm applied to the 3D stacked obtained after the after the shift and sum. So, okay, a lot of 3D information. Okay, if it is the convolution, it needs more time, but you can capture in real time. Let me tell you that in the past few weeks or months, we have developed a new product. It is published later. I will show you when or where. A handheld and cost-effective Fourier Lightfield microscope. This is the prototype made with some elements from Tor Labs, some elements from Raspberry, and okay, it is working here in real time. So okay, here we are moving the sample with the fingers. So this is the Raspberry card board, and this is in real time. And this is an example of the images you can obtain. The M12 lens, that is very cheap. You can pay for it less than €5, and the sensor is cheap. Okay, and okay, we are now working in a kind of let's say handheld prototype with other kind of obtained with a 3D printer. Okay, with the with the wires, with the focusing elements, connectors, and so on. This is something like 8 centimeters, 4 centimeters, and 5 centimeters. So, okay. Our contribution to Fourier Lightfield. Okay, we have contributed from our first paper, and here you can find some the microscope IPs, the handheld. You can find the algorithms we have been proposing to this technique. Of course, we are not the only people working on this technology. I have identified up to 6 groups who are working now in the development in this technique. The most active is this group from the Georgia Tech. They have published also a lot of papers. These are the group who propose to use not with 3 images but with two. The group from Laura Waller, the group from Kai Wong, this group from MIT, Boyden, from Cambridge, O'Halloran group, from UCLA. And with this, I finish my talk. I hope it has been of interest. Of course, you can contact me to more information, or I think now we have time for questions if you want. So thank you very much. I hope you are there, because I couldn't see myself. So, pointer is not visible. Okay. I'm sorry. Because of the pointer, I didn't know this. because I don't know why I was not seeing the presentation at the same time. I didn't have access to what you were watching. So sorry for the pointer. So is the chairman around? Is there any question? I cannot hear anyone.
The chairman is not in the group, so
Okay. So as far as I know, the recording of the tutorial will be available some months. So then later I will speak to people from the from FOM and will make the PDF available. The only thing is that in the PDF there will be no movies. But apart from that, I will make available the tutorial. Could you comment on resolution versus depth in Fourier Lightfield? Yeah, resolution is resolution versus depth is so when I put it in presentation time, I cannot see the chat. So I will replay and then I will come back to the chat. Okay, 1 second. Okay, 1 moment. Here. So as you can see, the formulas associated to Fourier Lightfield microscopy and the formulas associated to conventional microscopy are the same. The main difference is numerical aperture is changed by effective numerical aperture, and the objective magnification is changed by overall magnification. This overall magnification is much more smaller than this. So it means that in Fourier Lightfield, the pixelation is much more important than in conventional microscopy. And this is at the moment this is the main bottleneck. So we should try to go to smaller pixels. About that, as far as we have experimented, you can see here. Yeah, the depth field is pretty good. It's pretty good, but in the same relation as here, as you know, the smaller resolution limit, the smaller the depth field. So it is normal that here, for example, you have a high depth field. Why? Because you are dealing with poor resolution. So let's say that relation is the normal, not very special relation, it's normal relation. So the better resolution, the worse depth field. But mainly it follows normal relation, not very special one. Yeah, how does image brightness compare between native and Fourier Lightfield microscope? Yeah, we haven't made this study because okay, we simply have adjusted. But from theoretical point of view, we are working with smaller numerical aperture, and therefore we are collecting less light. So yes, we need more light. We need more light because, for example, this 0.65 numerical aperture is converted in 0.2 effective numerical aperture for any of the elemental images. So yeah, if you are in the border, yeah, you need more light. Okay. I think that the chairman didn't show up. I don't know if you are around or not. Otherwise, I think that we can conclude with this time. And thank you very much for all the congratulations I have received through the chat. I will speak to the organization on how to make the PDF available. So some movies will be lost, but apart from that, I think you will have all this information with you. Okay, so thank you very much to you all, and okay, I'm gonna leave. So bye bye, ciao. Thank you very much.